Continuing 6.1, an introduction to rivers. Velocity, discharge, erosion, and deposition. Rivers are the primary transportation and erosion agent in the rock cycle. As you can imagine, all those streams all over the world carrying all those loads. The picture on the left shows that even in dry areas, streams are the dominant carver of the landscape. The stream valleys are all over the mountains. The picture on the right shows a stream in a canyon that it carved itself. It took a long time, but all that rock that used to fill up the canyon has slowly been washed and carried downstream by the stream. Impressive, huh? Bed load, suspended load, dissolved load, all carried and pushed by the stream down to a base level, some depositional basin somewhere. The amount of erosion and deposition depends on stream velocity and discharge, as we've said before. Discharge is defined as volume of water that moves past a point in a given time, or the velocity of the water multiplied by the cross-sectional area of the stream. By cross-sectional area, we mean the area perpendicular to the flow of the stream, not parallel. We assume that the area that we are studying has a constant discharge, i.e. no tributaries entering our stream, no distributaries exiting our stream, and no significant changes due to groundwater seepage into or out of the stream. With that assumption, velocity changes are due to changes in cross-sectional area. I'll show you. But first, look at the picture on the left. Here's some guys getting the measurements needed to calculate discharge. They are measuring the width of the stream, as well as the depth and velocity in several places across the stream. The figure on the right shows the stream geometry we will be considering in our calculations. Nice and rectangular. Again, we assume that the area that we are studying has a constant discharge, i.e. no tributaries entering our stream, no distributaries exiting our stream, and no significant changes due to groundwater seepage into or out of our stream. There is a velocity vector, the v with the arrow, indicating that the stream is flowing in a particular direction, probably downhill. And there is a cross-sectional area indicated with a big A. Since we have a rectangular stream, the cross-sectional area is calculated by multiplying width and height, area of a rectangle. Familiar? So let's go to a piece of paper. Discharge equals volume divided by time, which equals velocity times the cross-sectional area. Area will have units like feet squared or meters squared, some type of length squared. Because we are multiplying two lengths, width times height. Velocity is like speed, but with direction. The units will be similar to speed limit units, with length per time. On the highway, our speed will be near 60 miles per hour. Miles is our length, and hour is a unit of time. In 1 hour, I go 60 miles. In streams, the units are still length per time, but usually we measure lengths as feet and meters, and time units, such as seconds and minutes. So the velocity of the stream will commonly be in feet per second or meters per second. Let's pretend that our stream discharge is 20 cubic feet per second. Remember that our discharge is going to remain the same. So let's see what happens to our velocity and cross-sectional area as we play with some numbers. For starters, let's say our velocity is 10 feet per second. So the cross-sectional area is 2 feet squared. Let's say I want a slower stream, slower velocity. Perhaps I want to wade on a bed load with finer sediment or something. Discharge is the same. "20 feet cubed per second. Velocity is slower. Let's say by half, so 5 feet per second. So what happened with my cross-sectional area? It got bigger. It actually doubled to 4 feet squared. Right. Five times 4 equals 20. Now let's step back and see if this makes intuitive sense. Ever gone river rafting? If you haven't, stop everything and go. Now that you have all gone river rafting, let's think about the river. Where were the scary parts? What did the valley look like? Was it narrow or wide? Was the stream narrow or wide? Was the stream velocity going fast or slow? Where were the relaxing parts? Where you looked at the wildlife and ate snacks and drank too much? Was the valley narrow or wide? Was the stream narrow or wide? Was the stream moving fast or slow? Chances are the scary parts were where the stream was narrow and fast, and the relaxing parts were where the stream was wide and slow. Does that fit the numbers? Discharge, constant. Fast velocity means smaller cross-sectional area, which has a dimension of width. So velocity means a larger, slow velocity means a larger cross-sectional area. Yeah. Do you believe me? Does this fit with your real-world experience? Now, one more thing. I need to show you that volume per time is the same as velocity times cross-sectional area. So first we have time. Units like seconds, minutes, hours, etc. Easy. Next, volume. We could use units like gallons and pints, etc. There are actually lots of volume units. Another way to measure volume is by lengths, cubed, like as in the volume of a box. We have a volume composed of width, height, and depth. Remember geometry, 3 dimensions. Three dimensions, 3 lengths, multiplied, give us the volume of the box. So I'm going to use feet to measure my width, height, and depth. I can use whatever length I want, and someday I might want to use meters, but today it's feet. I could use miles, it would just be a bit awkward. So feet for width, feet for height, feet for depth. Feet times feet times feet equals feet cubed. I have a volume. Feet cubed per second, and I have a volume per time. And the measurements for discharge. Now let's look at velocity times cross-sectional area. Velocity, feet per second. Cross-sectional area, feet times feet. Or feet squared. Feet squared times feet, or feet times feet is feet cubed. And it's still all divided by time. See, volume per time equals velocity times cross-sectional area, which equals discharge.